So this work attacks the classic problem of image segmentation and figure ground organization. So we want to take a single image, partition it into regions, and then order those regions according to figure ground or occlusion layering. So here red denotes near and blue denotes far. And just to start off with some results, our system output is fairly close to the ground truth. So we set up this simultaneous segmentation and figure ground as an embedding problem. And here we want to take every pixel in the image and map it into some unit interval so that location in this interval corresponds to absolute figure ground layering. And then we can get a figure ground map for the entire scene. We also want the property that proximity within this embedding interval corresponds to grouping in the original image. So if we cluster in the embedding space, we get back a grouping of pixels into regions in the original image, and thus we get figure ground plus segmentation as output. Okay, so the embedding system works as follows. We start off assuming we can describe pairwise relationships between possibly distant points in the scene. And these pairwise relationships are the form of, we want to know if pixel P is in front of pixel Q, or if it's in the same region, or if it's behind it. We also may have a varying degree of confidence on each of these predictions. And then our embedding task is to recover a globally consistent interpretation that is reflects as close as possible these pairwise relationships. And so the way we're going to implement this is to actually train a convolutional neural network to directly estimate these pairwise relationships. And this differs from a lot of past work on image segmentation that, for example, passes through an intermediate step of predicting local edges. Here we're just directly estimating local relationships between arbitrary points in the scene. But for computational efficiency, we'll not use all pairs of points, but use a sparse multi-scale connectivity pattern to determine the pairs we want to relate. Our actual embedding procedure is a little more complicated. I'll skip through most of the math here, but the point is that instead of embedding into the unit interval, we've stretched this unit interval into the unit semicircle of the complex plane. And figure ground now corresponds to angular rotation in the complex plane. The reasoning behind this is that normalized cuts actually falls out as a special case of this embedding system. So angular embedding is grouping plus ordering, whereas normalized cuts is just grouping. And this extra ordering aspect we're using to represent figure ground. There's an interpretation of these complex valued affinities in terms of figure ground displacement. And we can actually reparameterize our system so that the quantities we need to estimate with a CNN are simple probability maps of two types. The probability that P and Q are in different segments, and then a conditional probability of figure ground transition. So we set up an architecture to just simply produce these probability maps as output. So we have a probability map per offset in our multi-scale stencil pattern. And each probability map is the size of the original image. So the entire system together looks like this. We have an image, we pipe it through this affinity CNN that predicts these probability maps. They're assembled into a complex valued affinity matrix, which is piped through angular embedding to give us a figure ground and image segmentation. Please come by our poster for more results and about cross-domain generalization and object pop-out.